to thank you all for coming to our second lecture of a new series of radio astronomy talks. We are fortunate that we have support from the late George Halbern, as well as support from Sierra, the Department of Physics and Astronomy, and WCAS. I want to also mention that we heard the sad news that George Halbern passed away suddenly last week, and without his support, this there would have not been a series of radio astronomy lectures. And for this, we dedicate this sort of series of radio astronomy to the memory of George Halbern. But today we have our second speaker. We're very pleased to have Al Wootten from National Radio Astronomy Observatory. Al has been a powerful force in the development of the most ambitious project in ground-based astronomy and or NSF-supported astronomy. Apart from being the project scientist, Al has also had numerous scientific and technical contributions over the years. His scientific interests include star formation, astrochemistry, cometary composition, and evolved stars. He is involved in studies to determine the structure of protostellar cores through observations and modeling of molecular emission. He's also studying the deuterium isotopic composition of cometary molecules and of the chemistry of cometary coma in general. He is particularly interested in how ALMA confront the problem of imaging these large, extended, cool objects in the sky. Al went to the University of Maryland as an undergraduate, received his PhD from the University of Texas in Austin in 1978. He was Robert Welch Fellow at the University of Texas in Austin before going to Caltech as a postdoc. He joined National Radio Astronomy Observatory in 1984, and he's been there since. He's an adjunct professor at the University of Virginia. In 2004, he became the ALMA's science team leader, and he's now project scientist of North America. And today we're happy to have him, and he's going to talk about the remarkable instrument, ALMA. Take it away.
Okay. Thanks, Farhad, and thanks to everybody here for the invitation to come. It's been a great couple of days. I'll be here until sometime midday tomorrow if anybody wants to talk. Sorry to hear about the passing of George Halbern. So I'm going to talk about ALMA, the Atacama Large Millimeter Submillimeter Array. It provides us with a new millimeter wave view of the universe at high sensitivity and high resolution. Much like the Very Large Array, uses the same techniques that Jim Condon discussed in his lecture a couple of weeks ago. One difference is that ALMA, coming along some decades after the VLA, we were able to learn from the experience of the Very Large Array. We're also addressing a different wavelength range, going up to millimeter wavelengths. And at millimeter wavelengths, the sky tends to have more very extended objects, and your antenna beam tends to be smaller from any given telescope. And so you need an ability that the VLA doesn't have, and that's to be able to image large extended objects. For that reason, it's a revolutionary imaging and spectroscopic telescope system for millimeter and submillimeter astronomy, but it didn't just come from nowhere. We built on the VLA to improve the imaging quality and the flux recovery so we could image these very large objects. And it built on pioneering technical and development research conducted all around the world at NRAO, at the SMA of the Center for Astrophysics in Cambridge, IRAM, a consortium of German, French, and Spanish interests, the Nobuyama Millimeter Array in Japan, CARMA, which was until recently located at California. The University of Chicago was a partner in that, and the James Clerk Maxwell Telescope that was a effort of the UK, Netherlands, and Canada. So by bringing together parts from all of these telescopes' experience, we were able to build a telescope that was even more powerful than anything that had gone before, and more expensive, as Farhad said. So it consists of 66 reconfigurable high-precision antennas. I'll talk about those a little more in a minute. It's located sort of in the middle of South America in this Google Earth zoom, which was taken back in March 2010, I believe, maybe 2011, when there were only a few antennas at the site. So now we have many more. We have all 66 up at the high site. It operates eventually over a wavelength range from 350 microns to 8.6 millimeters. The site here that you're seeing is at 5,000 meters elevation, 16,500 feet in the Chilean Andes. This has been a very difficult site to work at, but it provides excellent clarity of the atmosphere and provides unprecedented imaging and spectroscopic capabilities at the high frequencies at which we want to work. It's a global partnership, so the shared cost was about $1.3 $2006. North America spent about $500 million, 37.5%. The North American section of this is the US, Canada, and Taiwan, oddly enough, for complicated reasons. Europe is 37.5% through the entity formerly known as the European Southern Observatory. And I have a much longer name than I have on one of these slides that I can never remember. East Asia, 25% from Japan, Taiwan again, and Korea, in collaboration with Chile as the host nation. So basically, Chile didn't contribute towards the construction. They contributed the site, and in turn, we rent the site from Chile for an amount of money, and they get 10% of the observing time. The site is exceptionally high and dry, and those 66 telescopes are comprised of several different varieties of telescope that I'll show you. Basically, there's a 12-meter array, which consists of 50 12-meter antennas, and then a Japanese contribution to the array that came along later, particularly to help us image these large extended objects, is the Atacama Compact Array, and it has 12 7-meter antennas and then another 4 12-meter antennas. These 12-meter antennas are dedicated to use as single telescopes to map extended emission. So ALMA was finished about a year ago. It came in under budget. I think all the partners had a little bit of money left in the kitty after it was over. So we can deploy these antennas in configurations between 150 meters if you pack them as close together as you can get them, or 15 kilometers, which is about the size of the borders of Washington, D.C. So think of the D.C. Beltway, if you've ever been there. There are 192 possible antenna locations within that 15 kilometers, so we can place any antenna on any pad, but usually we reserve those for the 50 12-meter antennas, and we have a separate 22 antenna locations for the 16 ACA antennas on a shorter baseline, as I'll show you in a minute. So at the 15 kilometers, right now ALMA is in fact in that 15 kilometer configuration. The angular resolution at the highest frequency might be as good as 50 milliarcseconds yet. We haven't yet realized that, but maybe during the next month or so we will. There are 10 frequency bands. Here I have I gave you the limits in wavelength a while ago. Here they are in gigahertz, 35 to 950 gigahertz. All the data that comes out of ALMA is archived. The archive is available after a year proprietary period. That data is available to anywhere. Unlike, for instance, the Very Large Array, we provide reference image. We actually go through and image the data, and that's available in the archive also. The data gets to the archive by going through pipeline processing. At this moment, we can only calibrate the data through the pipeline. The imaging pipeline is still under development, and it's always next month that it's going to be ready. But right now, the data is imaged by folks like yours truly in Charlottesville. So it's an effort really of many nations for all astronomers. I think we've made the data much more accessible by providing actual images as the data product. So it's a partnership, as I said, of those countries. The funding, I have to say, comes from the National Science Foundation in the US and also from the NRC in Canada, about 7.5%. And a smaller amount from the National Science Council of Taiwan for the North American side. ESO, it all comes from, here's the long name, ESO, a European Organization for Astronomical Research in the Southern Hemisphere, formerly known as ESO. In East Asia, it's the National Institute of Natural Sciences in Japan. in cooperation with Academia Sinica in Taiwan and CASI in the Republic of Korea. So why are we interested in the millimeter, submillimeter spectrum? Back in 1983, the IRAS satellite went up and gave us our first view of the far infrared. And it discovered that there were a number of extremely bright objects there, for instance, ultra-luminous infrared galaxies, and was able to map out the cosmic infrared background, which is the central of the three curves here. The one on the left is the optical background.
You have a pointer?
Yeah, I do. The one on the left, all I have to do is find the on button. There it is. Okay, so this is the cosmic optical background over here, and this is the microwave background, the relict radiation for the Big Bang. So you can see that the discovery of this peak showed us that these millimeter, submillimeter photons were the most abundant photons in the cosmic background, and in fact in the spectrum of the Milky Way and most spiral galaxies. We knew about the 3K cosmic microwave background, but it was imperative to explore what gave rise to this infrared background. So I'll spend a little time talking about this. The ALMA range covers only the long wavelength portion of here because the Earth's atmosphere blocks the far infrared from getting down to the surface of the Earth. Okay, we had three key science goals in ALMA, and in the ALMA science team, one of our first jobs was to come up with key science goals, get the community to agree on them, and then derive all the technical specifications for the instrument from these science goals. So the first was to detect spectral line emission from carbon monoxide or carbon-2 in a normal galaxy like the Milky Way at a redshift of 3 in less than 24 hours. And when we first came up with this one, it was in fact back in 1983, and it was a normal galaxy at Z of 1. We had not yet detected any galaxies at any high redshifts. And so this was a fairly visionary in the beginning, and as I'll show you, I think we've met this now with ALMA. We wanted also to be able to image the gas kinematics in protostars and protoplanetary disks around young sun-like stars in the nearest molecular clouds, which are about 150 parsecs away. So this means we have to get very much sub-arcsecond resolution, best of all if we can get down to 10 milliarcseconds or so. So we've been able to get this kind of resolution, not shown in, there's a longer version of this sentence which mentions magnetic fields, and so far we haven't yet gotten around. We haven't been able to commission the polarization aspects of the observatory to such an extent that we have examples of that. And lastly, we want to be able to provide precise high dynamic range images at an angular resolution of at least 1/10 of an arcsecond to match Hubble. So this first one is basically a sensitivity goal. We want to have sensitivity. In order to get sensitivity, you need collecting area, particularly to get spectral line sensitivity. The spectral lines emit over a limited bandwidth. For the continuum, you can just increase your bandwidth as much as you want, get more goody, and be able to increase your sensitivity, but it's harder with the spectral line. All you can do is increase the surface area. So that's set the surface area of ALMA basically at 6,600 square meters, about almost 2 acres. We want to be able to image. These two are both imaging ones, and to make good images, you need to have sample the Fourier plane that Jim Condon talked about, the Fourier transform plane, as good as possible. So it helps to have a large number of telescopes. Each pair of telescopes gives you a baseline. From having the most baselines possible, you can produce the best images because you're able to fully sample the Fourier transform of your image through Earth rotation synthesis. I think most of this I've said already. So I wanted to mention here that ALMA can also act as an element of a global network through very long baseline array by tying it in with other antennas and other positions on the Earth. And so in fact, we're just beginning now to do the first observations with ALMA this way. It will be, we'll have our next call for proposals in April, and it will be open to the public to propose very long baseline observations for which basically the ALMA is an important element in a telescope which has a diameter about the diameter of the Earth, using these other telescopes. So here are the antennas. Each one of these is about 5 stories high and weighs about 100,000 pounds. There were 3 different designs. Each region had a large chunk of money going into this, and so the industry in that region had to get something out of it. And so the Alcatel consortium in Europe consisted of companies in Italy, France, and Germany, and built this antenna, of which we have 25 on the site. In North America, General Dynamics Satcom Technologies started out as Vertex in Texas. The antennas themselves were built in Texas, but the company was taken over by General Dynamics, and its actual headquarters is Vertex Antenna Technik in Duisburg, Germany. Mitsubishi Electric Corporation in Japan built the 12-meter telescope from Japan, and in addition built the 12 7-meter telescopes in the smaller array. So all told, there are 66 of these, 54 of the larger telescopes.
Question?
Yeah.
I mean, it's plain from your picture that they're not identical.
Yes, but they perform to identical specifications.
Okay, so wasn't it, I mean, I would guess naively that it's more cost-effective to have one design and farm it out to 3 different corporations.
Yeah, but it was politically impossible. So yeah, the realities is that was our original design, and so we came up with the specifications.
Yeah.
And then it became clear that unless these contracts were about $190 million for each one of these, that it would be politically impossible for ESO to allow the contract to go to a company in Texas, even if it was run by a branch in Germany. And the same with Japan, and the same with North America. So they're all built to identical specifications, and of course we came up with a wonderful argument that this was the way it should have been all along, because if you've got several different designs, each one will behave slightly differently, and everything will even out in the long run, and you might end up with a better instrument than if you had 50 identical antennas, all of which, for instance, had a defect. So in fact, each one of these telescope designs has its Achilles heels, but in general, they all perform to the same specifications. So they have a 25 micron surface, and they can point to within 2 arcseconds anywhere in the sky. Okay, so we move these at the very large array. There's a train and a railroad track that moves the antennas around, but that limits you to where you can move the antennas to basically along linear elements, and that makes features in the image plane then which are undesirable. And so we thought the best imaging would occur with our smaller telescopes if we could move them around with a transporter. So we have 2 of these transporters together with the antenna. This weighs about 500,000 tons. You want to get out of the way when it's coming towards you. And these then transport the antennas and move them between the antenna pads. So here I have a sort of a topo image of the high site. You can see that in the center it's very flat. There are positions here for about 100 different antenna locations. Up at the north, you can just begin to see the region where the compact antennas sit, which is seen better down here as an extension off to the north. So the main building is just about 1 kilometer away from the center of the array here. And then they can be deployed, and you can look, if you can see, these are in a sort of a quasi-spiral configuration. There are several different patterns which you can use, but the spiral, it turns out, has the fewest imaging artifacts when you actually go to use it. Then when you get to the largest array out at 15 kilometers, you're constrained by old volcanic cinder cones on the site and by deep crevasses that cross it. And so there we have a sort of an arm that goes out in 3 different directions here, but the antennas are not in a directly linear arrangement on those arms. Yeah?
How long do you guys usually allow for reconfiguration, and does that kind of affect how you do proposal cycles?
Well, when we planned the configuration, we planned to have 2 crews on the antenna transporter. Basically, in Chile, everything works in what's called a turnout. You work 8 days on the job and 6 days off. So if you have 2 crews, then you've always got somebody there. We have 2 transporters. They're always there, able to move antennas around. But it turned out that each one of those crews costs $500,000 a year, and so, well, that was one of the first things to disappear. And so the crews come up for 8 days. And the idea originally was that because this is a dangerous place to try to operate machinery, 16,000 feet, we would try to move a couple a day and gradually go from a compact array to the most extended array. But that turned out not to be very practical. So now it moves in sort of a burst mode. Right now they're, from starting on October 1st, we started our new cycle of ALMA observations. We started in the long baselines, and they started moving antennas out, and it was supposed to be done during the 8 days of the turno, but there are 3 antennas that are still not out there because it's El Nino time, and there's a lot of snow on the site, as you'll see in a minute. So at any rate, it's difficult to move all the antennas out. We had them in a very compact configuration. Moving them to the largest configuration can take a couple of weeks. Here's a picture from last week. Remember, these antennas are 5 stories high and 100,000 pounds, and there's one in the picture here. But they're really spread out over a fairly inhospitable, here it is, landscape. And we have a lot of snow, especially when there's an El Nino, which piles up and has to be bulldozed. We have to clear off the antenna pads to move the antennas. So that's one reason it's taken so long this year to move to the high long baseline configurations. So they're kind of lonely out there, and all you can do is hope they keep working because it's a pretty big effort to try to get up there and go to these spread out over a region of the Washington Beltway and fix them if they're not. So far, they're pretty reliable. So the signals, I'll talk to you about the receivers in a minute. But the signals come together to a key central element design, the correlator. This is a special purpose supercomputer that combines the digital signals from each antenna. So the signals are digitized at each antenna, all come together to this correlator that sits also at the 16,500 foot site. This produces a lot of heat. Air conditioning is not particularly efficient at the high site, so this is a huge cost in electricity to run this thing, but nonetheless it's in its building. It has oxygenation, so that I didn't show a picture of the back of this. There are a lot of wires in the back, but you want to make sure you put them in the right place. In order to do that, it's best to have a little oxygen. So it's a fairly complex building. I think it's the highest technologically advanced building on the planet. This machine then does 17 tera operations per second to bring together the data from all those baselines. This is also because it's at 16,500 feet. You can't have a normal hard disk where the head floats on a cushion of air because there isn't that much air up here. So everything is done on solid state memory up here. Then it goes down to the 10,000 foot level, which is where most of the people actually sit. So there are 2 correlators. One is the main correlator with 64 inputs, a separate one built by Fujitsu in Japan. For the Japanese array, provides some independent processing.
Quick question.
Yeah.
It had to be at the site, the correlator. You couldn't transfer the data to do the.
Well, you could, but each line is producing a tremendous amount of data, and it would have cost more. So the easiest thing to do is correlate it at the high site. Even though we have to air condition the building, you need some sort of home base at the 16,500 foot level. So this also has a refuge in case a storm comes up and somebody's trapped up there. So it serves many purposes. Question in the back?
So how are you sending the digital data from the telescopes to the correlator?
Okay, so I was going to do that in a minute. The data is basically the front end. In the telescope, we digitize the data and then send it over fiber optic to a patch panel that's located just in a different room up here in this building, and bring it all together there and then feed it into the correlator. From that point, the correlated data then goes on fiber optic down to the 10,000 foot level where it goes into the first archive. And then originally all we had was a microwave link to the rest of the world, which is a bit fragile. But now we have a fiber optic cable that then takes it to Santiago. It then goes to Sao Paulo and off to the rest of the world. I think I've got it.
Another question.
Yeah.
Who built this correlator, and roughly how much did it cost?
Okay, this was built in Charlottesville, the Fujitsu one in Tokyo, and its cost was about $13,002,006. Okay, so this was done, this is a 2003 design. So it's basically ancient now, and we're looking into ways to upgrade it, as this little bullet says here. So it works. Here are 60 antennas, baselines, 1,770 baselines at 400 gigahertz towards a quasar 3C454.3. And so what you have down here in the middle are the autocorrelations, the correlation of each antenna signals with itself. And then we have cross correlations between each pair of antennas on the side. Here we have the phase part of the information, and here we have the amplitude part of the information. And so together, all this data can be combined to produce an image of this quasar, which is, of course, a point source. Not a real exciting image, but nonetheless. That also makes for... so these phases should all be flat in the best of all possible worlds. But in fact, you know, we're under an atmosphere that's moving across them. That's creating gradients. They're electronic gradients. And so you'll see that these all have a bit of a slope to them. It's part of the data reduction process to try to remove those slopes. So here's the atmosphere as seen from the high site. Our goal was to be able to observe any portion of the atmosphere where the transmission was 50% or better. And so we achieved that by having 10 receiver bands. Not all of them are on the instrument now. Each receiver band consists of 73 state-of-the-art receivers. They're fairly expensive, and we couldn't afford them all in the beginning. But we have a development program through which we are finishing the complement. So the red ones, bands so-called 3 at 3 millimeters, band 4, 6, 7, 8, and 9 are finished. Band 10 is more technologically difficult, and so we left it until the end. It's now been completed, and it's now on the array, and we sought observations from PIs for band 10 at the last call for proposals. Bands 1 and 2 are not yet on the array. Band 1, there's an East Asian consortium together with North America and Chile, which is building the first prototype. So we hope to have these deployed on the array by 2019. Band 2, there is a group in Charlottesville and a group in Florence that are looking at the construction of a band 2 receiver. We are building a prototype in Charlottesville that could be on the array in 2022 or 2023. We'll have to decide on the details. Okay, here is the doer containing the front ends. A little fuzzy here, but there are, you can see, 10 spots. Each of these is a cartridge about this big around, this tall, which slides in with the front end electronics. There are 2 vacant places here for the bands 1 and 2. So there are no moving parts here. Everything is electronically tunable, which is a good feature when you've got them spread over 15 kilometers at 16,500 feet. We have state-of-the-art receiver performance. At the time when we negotiated the contracts for building these in 2003, there was no receiver that could meet any of the specifications. And so each of the groups that built these receivers was able to build their receiver, deliver it, and they were all installed in the array in time for the end of construction. So each of these has dual linear polarization, a bandwidth of 8 gigahertz per polarization, and each polarization is to split up into 2 gigahertz basebands. These are all line replaceable units. They just slide out if something's wrong with them. They can either be repaired on site in Chile, or if there's a more complicated repair, then they can be sent back to the manufacturing, in our case, NRAO, for retrofit. So just below this is the digitization of the signal. So it's 3 bits, 8 levels. From each one of the antennas, we get 96 gigabits per second that then goes to the correlator to be correlated. So the signals are cross-correlated for a large number of delays and all possible antenna pairs, resulting in that matrix that I showed you a while ago. So the operations, a few words on how we run this thing. They're led on behalf of North America by the National Radio Astronomy Observatory in Charlottesville, Europe by the European Southern Observatory, East Asian by the National Astronomical Observatory of Japan in Mitaka, just west of Tokyo. And the joint ALMA observatory is responsible for the operations in Chile, which take place at 3 sites. The array operations site is 16,500 feet. I told you antennas correlator. The operations support facility is where all the people are. And so there are a couple dozen people at this level, including the astronomers that run the array, the maintenance technicians that keep it running, and support staff. And then the Santiago central office, which is in Santiago on the same grounds that ESO's headquarters is there. So all communications with ALMA occur through the website almascience.org, which is where you go to look at the archive.
Can I ask how close are the operations support facility to the array operations site? Is that all in the same place, or is it a lower?
The array operations site, if you want to drive up there, for instance, well, we had to build a road because this was in the middle of nowhere. And so the road is about 44 kilometers long. It's about 15 kilometers to the operations support facility. The next 30 kilometers is to get up to the high site. So to drive it takes about 40 minutes.
So what's the elevation of the operations support facility?
Chilean law makes you pay people more money once they're above basically 3,000 meters. So it's just below 3,000 meters. That's a mining industry law. Okay, so once the data, described how the data gets to Santiago, that's the central archive. Then that's replicated basically within an hour or two through the internet, which goes from Santiago to Sao Paulo, and then comes up to Charlottesville, goes to Munich, and goes to Tokyo. So basically, in Charlottesville, we can see the data that ALMA took within an hour or two afterward. Okay, whoops. So any rate, so then we go to the astronomers, which is you. And we have over 300 publications now since the start of operations. And these are just some of the colorful images. It's one of the goals of ALMA was to produce images. I thought I needed to show some that have been produced in those publications. So those publications have closing in on 3,000 citations now. And I think they've produced some exciting results, which I'll talk about now. Okay, so I'm going to start in the distant universe and sort of come closer. So as I mentioned, one reason we built ALMA was the discovery of that cosmic infrared background, which was basically of unknown origin at the time we built it. Shortly after that, the JCMT had a imaging instrument called SCUBA, SCUBA was on the JCMT, which began discovering millimeter galaxies where at least some component of that infrared background. And so here is a picture of the spectral energy distribution of a typical galaxy. This is actually M82 as observed by ISO, which was a satellite that went up in the early 90s. It didn't observe shortward of here, so this is all the ISO spectrum. But then M82 is not a particularly impressive galaxy. And so we pumped it up to have the luminosity of some of the luminous infrared galaxies that we observe. So this gives us a sort of a cartoon spectral energy distribution, and it includes some of the bright atomic fine structure lines of oxygen, carbon, and nitrogen, which then get redshifted. As we move to higher and higher redshifts, they move then through the ALMA bands, which are shown by these stippled areas. So you can see that when the object gets redshifted, it moves to the left, and although it gets dimmer, a brighter portion of the spectral energy distribution gets moved into the band. And thus there's a sweet spot here where no matter what the redshift is, up to a redshift of 7 or so, you might expect that the brightness of the galaxy as seen by ALMA will remain the same. So this is an excellent machine for being able to look at very high redshift galaxies. So here we see the ALMA sensitivity levels for roughly a few minutes of observation. And you can see any object like this could be observed even in the distant universe. And in particular, these very bright carbon-2 lines, which emit about 1% of the total luminosity of a galaxy, will show up in these windows. So that's the big signpost line for looking at the high redshift universe.
Sorry, what kind of spectral resolution do you have in that region there?
So the spectral resolution is set by the 8 gigahertz bandwidth, the correlator. And so basically, in kilometers per second, we can go down to very small, but the coarsest resolution is in the order of 25 to 50 kilometers per second.
So you can also get the redshift from carbon line as well as the continuum,
Right.
the
So I'll show you.
SED, so you have both.
Right. But the SED here, I should point out, I put in bold letters here and forgot to mention it, that this is a local galaxy. It has solar metallicity. And of course, if we're going to look at things at a redshift of 12 before there were many stars in the universe, the stars hadn't produced the metals in the abundance that we have in the local universe. So that to some extent, this portion of this diagram is a bit of a lie. Lower metallicity galaxy spectral energy energy distributions might be depressed at higher redshift, and I'll talk about the evidence for that next. Okay, so another feature of ALMA is that although we can observe the high redshift universe, if we were to have a single antenna, perhaps of the size, this is from Herschel, in orbit, or perhaps on the ground from the size of any of the existing large antennas, the galaxies would eventually bleed together because of the limited resolution that a single dish telescope has. And so the Herschel image here shows very well, I think, in this famous Goods North field, how the galaxies begin to bleed together when you get down to the deepest sensitivity levels. But because ALMA has basically resolution dialable by moving the antennas further out, ALMA doesn't have any confusion limit, and so we can get a clear view of each galaxy individually. Okay, so I'll show you some examples of that. Furthermore, in the beginning, the periodic table was pretty boring. All it had was hydrogen and helium in it. Now, the chemists would argue that this was boring chemistry because Oka, loves H3+, H2D+, H2, HD. There are a lot of interesting molecules you can make just with these two. But eventually, the rest of the elements came along. And what we want to do with ALMA is be able to monitor the creation of oxygen through the atomic oxygen lines of O1 and O3, the molecules OH and water, which will be abundant wherever there is oxygen. And carbon, through the carbon 1, I showed you that carbon 2 line a while ago, a particularly important line, as you'll see. Molecules carbon monoxide, CH, CH+, and perhaps even isotopic carbon. Nitrogen is a little more difficult to make. It's made in evolved stars, so it might not be made in abundance right at day 1, but it's visible again through two nitrogen 2 lines, one at 205 microns with a redshift of just 1 or so begins to enter the ALMA bands, and another line at 120 microns. And the molecules NH and N2H+. And of course, all these molecules together make up what we cheerfully call dust, the aggregate emission of all these elements that agglomerated into solids of various sizes. And this is what was emitting to produce the spectral energy distribution that you saw a while ago. Okay, and these are made in supernovae, so I thought this was an appropriate time to show you an ALMA image of supernova 87A, closest supernova to occur during our lifetime in the Large Magellanic Cloud. And so one of the first experiments was to turn ALMA on this. Remember the Space Telescope saw this beautiful diadem of excited lines where the shock wave from the supernova was moving out from the supernova. And in the center of that, we found a region of dust. It was known that there was dust being created during the supernova, but we were actually able to measure it and its change over time, showing that material was still condensing from whatever came out during the supernova into dust, and so the dust mass of the remnant is actually increasing. And the same goes for the molecules. So this is showing the aggregate emission from the molecules. I'll show you the spectrum, I think, on the next slide, which sort of blew our socks off. I mean, we were not expecting this to be so easy. Basically, we set up the instrument to look at CO. Because the way the receivers are set up, there are two sidebands, so we're sensitive to two frequencies on the sky. If you set up the CO in one sideband, you happen to get SiO, another abundant molecule in the other one, and gee whiz, both of them were extremely strong, and in fact, we even had a hint of isotopic SiO in the other bandwidth. So these lines are about 2,500 kilometers per second wide. They're clearly occurring in the molecules that are in the ejecta coming out from the supernova remnant. This was at 1 millimeter. We also observed the CO at 3 millimeters to get some handle on the excitation. So we actually see nearby the elements being produced. Now, what happens in metal-poor galaxies? I showed you the cartoon showing the spectral energy distribution like M82 or ARP220 here. We don't know what the spectral energy distribution of a galaxy at Z of 7 looks like, but one analog might be what low metallicity galaxies in the nearby universe look like. And so in this plot, we show spectral energy distributions from galaxies with a number of different metallicities in the nearby universe going down to a dwarf irregular galaxy, which might have 20% of solar metallicity. And superimposed on here are some actual limits that I'll talk about in the next slide from ALMA at a redshift of 7 on galaxies, showing where these would occur in the spectral energy distributions if these spectral energy distributions applied at redshift of 7. So in fact, we don't detect any continuum emission from these redshift of 7 galaxies, which suggests that in fact they have a suppressed spectral energy distribution. So here are some of those distant galaxies. How do you know where to look? There are a lot of places in the sky one can point ALMA. This far, it's always been guided by observations of distant Lima alpha entities, Lima alpha being observed in the infrared. And so this galaxy is called Himiko at a redshift of about 7. It has a couple of features in it, and it's thought to be a galaxy, very early galaxy undergoing a massive amount of star formation. And so Himiko, Owing et al. Pointed ALMA at this in order to look for the carbon-2 and the dust continuum and found neither one. So that limit I put on the previous slide was in fact from Owing et al.'s paper, showing that it's suggesting that there wasn't very much in the way of dust emission or carbon emission from this galaxy. What's going on? Well, recently, maybe we're witnessing an assembly of the first galaxy. Recently, there was an observation of a second object, BDF 2399, also at a redshift of about 7, which lies here at the X. And the ALMA beam covered basically this whole region. And carbon-2 or dust, neither one were detected at the position of the Lyman alpha galaxy, but there was a clump about 4 kiloparsecs away, suggesting that perhaps what's going on here is whatever is producing this tremendous burst of stars, producing the Lyman alpha emission, is basically making the carbon in a higher ionized state than carbon-2, or ionizing the dust, so that we're just choosing the wrong probes for looking at the high redshift galaxy. So the story is still being written on these earliest galaxies. There are a few detections of carbon-2 now at redshift of 7, but that's just about it, no dust. Okay, so let's move on a little closer. At redshift of 6, and this is still within the first billion years after the Big Bang, there is carbon-2. This paper by Wang et al., also Wootten, looked at quasars at a redshift of 6 and was able to detect both the continuum, the carbon-2, and in fact map velocity fields out. And from the velocity field you can get a dynamical mass, and which suggests that these are 10 to the 11th to 10 to the 10th solar masses. So these are almost the same mass as galaxies like the Milky Way now, even at this time a few 100 million years after the Big Bang. So they found carbon-2 at the QSO, which presumably locates a black hole, which somehow has managed to form in that little bit of space since the Big Bang. But there were no other carbon-2 emitters found nearby. So there are a number of cases now of carbon-2 at a redshift of 6. Now here the continuum is detected, but the nature of the continuum is not really clear, whether that's really dust or emission of another kind from the black hole.
Can you measure the mass of the quasar or from the dust?
Yeah, from the velocity here, the mass of the quasar can be measured, and in fact that's how they determined that these are
assuming that
supermassive
it's
black
a
holes.
dust emission, can you actually get an estimate also what the mass of?
Yeah, you can compare carbon-2 is very difficult to get a mass from, but from the continuum you can also get the mass and compare it, and it's commensurate roughly. Okay, so but these are fairly small objects. Well, and so let's move a little closer now at a redshift of 5. So in this paper, very recently in Nature by Kapak et al., what they looked at were a number of galaxies at a redshift of about 5 to ask the question, are evolved galaxies present among the fainter star-forming population at high redshift? So with ALMA, they looked at a number of galaxies that were fairly normal luminosities. That is, a lot of the galaxies I've shown you so far have luminosities of 100 to 1,000 times that of the Milky Way. but these were in the order of 1 to 4 times that of the Milky Way. So relatively low luminosity. They detected the carbon-2 with ALMA in just 20-minute observations in all 9 of the galaxies that they targeted here, but only 4 of them in the dust continuum. So they found from the spectral line distribution and from the velocities that the gas is distributed in each one of these over scales of 1 to 8 kiloparsecs, again like a normal galaxy would be. There were diverse dynamics located. Some of these are fairly complicated objects. But these are apparently highly evolved galaxies of large stellar mass, a few times 10 to the 10th, a star formation rate of 3 to maybe 100 times that of the Milky Way. The present-day Milky Way is making stars at about 1 solar mass per year. But the thermal emission, that is, the continuum dust emission, is suppressed by a factor of 12 relative to galaxies fairly nearby. So this suggests there's a very strong evolution in the interstellar medium properties. These galaxies, remember, resemble those low metallicity systems that we talked about earlier. But evolved galaxies, not unlike the Milky Way, do seem to be present at a redshift of 5, so maybe we have met the first science goal of being able to detect carbon-2 in a normal galaxy in less than 24 hours. And in fact, we never dreamed it would be 20 minutes. How about nitrogen? Nitrogen is a secondary element normally produced within low-mass stars, not in the supernovae as much, and so we might expect its abundance rise in the universe to lag that of oxygen and carbon. So spectrally, it's traced by the nitrogen-2 lines at 122 and 205 microns, which emit about 5% of the carbon-2 intensity in the local universe. So we have to be able to get down to a fraction of the intensity of those carbon-2 lines that we observed in 20 minutes. So you need a bit longer integration. So Nagao et al. Did this in this phone number galaxy here, which is a starburst submillimeter galaxy at a redshift of 4.75, or about 1.3 billion years since the beginning, since the Big Bang. And they measured a ratio of about 5%, 4.3%, which is exactly what you see locally, for instance, in M82. So this suggests that nitrogen was already built up by the time the universe was 1.3 billion years old. So I should mention the carbon-2 line here is from a separate observation. There was an observation with a single ALMA prototype antenna is located next to ALMA and is operated by ESO on the high site. And so they spent some time looking for a carbon-2 in this object. I think they spent 50 hours to get a detection of carbon-2. These authors went back and observed it with ALMA, and it took a couple of minutes. So one of the first surveys was the so-called Apex La Boca something survey, ALS for short. They looked at 126 strong submillimeter galaxies that had been detected by Apex using a camera in the submillimeter. So here we have images of each one of these, which are basically false color, showing the infrared locations of the objects. I think it's pretty hard to see where the contours are, but the contours show where the ALMA emission was detected. And in not all cases was the ALMA emission located exactly on the far infrared, or the infrared emission, near infrared emission in this case. So that suggested that something was going on here, that the near infrared emission was not coming from the most of the mass of the object. Most of the mass of the object was emitting in the ALMA wavelength bands, and that these objects were complicated perhaps by dust in the foreground suppressing the emission at near infrared wavelengths. So they looked at 122 of these objects using 2-minute integrations to get the red contours here, which were deeper by a factor of 3 and higher resolution by an order of magnitude than what they'd been able to get previously. There was a separate survey. John Karlstrom has been running the South Pole Telescope, and they've been doing a survey around the South Pole, and so they came up with a number of millimeter bright galaxies. The brightest galaxies that you see are likely to be galaxies which are lensed by intervening galaxies, lending them their brightness. So they looked at 47 of these. There were 47 of them that they chose not to be coincident with known radio galaxies. And so they imaged these in about 1 minute with ALMA at 2 wavelengths, 3 and 8/10 of a millimeter. And here is an example. They found the blue is the optical image, and the red shows the ALMA image. And so you can see that many of these are clearly Einstein lenses, which are focused by the optically visible object in the center. So they then looked at these, since we know these have been magnified by some amount by the intervening galaxy, to do blind spectroscopic observation of 26 of these. 23 of them showed high redshift CO. 10 of them had a redshift greater than 4, which doubled the number of such objects known. And they found that the fraction of high redshift dusty starbursts was much higher than had previously been thought. So here are the spectra that they got from these, arrayed in rest frequency here for the redshift of the galaxy. And so you can see the CO lines pop out immediately. And for many of those, since the spectrum gets compressed, the higher the redshift goes, and so you cover more rest frequency territory, you can see multiple CO lines, which allowed you to right away determine the redshift and the identity of the lines. There are also some carbon-1 lines in here and some hint of some water lines. So what do the galaxies at Z of 3 or 4 look like? Do they look anything like the galaxies now? What you can do is sum up all these spectra to get a sort of a representative spectrum of a galaxy at that epoch. And so Spilker et al. Did that, and they came up with this spectrum, which looks very much like normal galaxies near to us now. Lines like CN, HCO+, HCN, water is hidden by the Earth's atmosphere, so we don't generally know much about its distribution locally in galaxies. Herschel has helped that a little. HCN here, a number of galaxies. Somewhere in here, I'm not sure I could identify it, is a 13 CO line. So the one difference that they were able to identify was the 13 CO line was a little bit weaker than they might have expected, given the 12 to 13 ratios in the local universe. But that might be just that the elemental composition of carbon hadn't matured yet. So here's one of the Herschel images showing a couple of very distant lens galaxies. In particular, one of these, number 81, was one of the first ones noticed. This was, in fact, observed with the Green Bank telescope, and its redshift was measured, and it was found to be at a redshift of about 3. So what happens here is there's an intervening quasar at a distance of a redshift of about 0.3. The light from the distant galaxy is almost perfectly lined up with it and is bent as it moves around it to provide a ring. And so this was one of the first observations made with the SMA. I think there's a similar observation from the Plateau de Ver interferometer of Iran, which show the ring-like nature of the emission once it gets lensed. And so we decided to try imaging this with ALMA, and we were able to image a beautiful ring. So I'm going to talk a little bit about this one. Here's the ALMA image. I think you can say that this is, in fact, a excellent, shows the imaging capability of ALMA to excellent advantage. In the middle of this is that quasar. Here's a superposed Hubble Space Telescope image, which is distorting the background galaxy. In this paper by ALMA Partnership, Lahakis et al. So here is the data split up into different wavelength bands that went into that composite image I just showed you. Also, there are 3 CO lines that were covered, 5 to 4, 8 to 7, 10 to 9. This is a fairly high excitation line, and so we might expect it to be weaker in cool gas, such as we have in our local galaxy. Down here is a spectral index map, and we have, in fact, an emission line of water that was also covered. So we have 3 spectral lines and water. So the only way to do this is with the great sensitivity that ALMA has. We could make an image in the continuum like the SMA did, but you can't get the spectral lines unless you have the collecting area of ALMA. So what can we tell about this galaxy? Because it's lensed, we're able to observe it at something like 400 parsec resolution at a redshift of 3, which is pretty amazing, actually. And here is the continuum image that was reconstructed. I think there are, last count, there were 8 or 9 papers written. This is data that we just put out and made available to the community immediately. And so a number of people took advantage of this. And of course, the first thing you do is try to reconstruct what the object looked like before it got imaged by the intervening quasar. And these are the results, at least at 1 millimeter and 0.8 millimeters. So you can see that the features are the same in each one of these. There are different structures here, but you have some faith that there are at least 4 or 5 clouds here that are seen in the continuum. So here we have emission, probably dust emission from molecular clouds. And we can then do the same with the line emission, as Swinbank et al. Did a little earlier this year, and took the carbon monoxide, here see the 5 to 4 carbon monoxide line, deconvolved it, and found that the structure of the galaxy that we are seeing magnified is a rotationally supported disk, a few times 10 to the 10th solar masses, rotations of about 320 kilometers per second. And these molecular clouds are sort of similar to the ones that Farhad looks at in the galactic center. They have very broad line widths, and the clouds themselves are fairly massive. And so these are not dissimilar from those we find in the galactic center of our own galaxy. Okay, and we can move on into a number of nearby galaxies. Again, the excellent line sensitivity provides a new window in the central regions of galaxies. And there are some 40 molecules mapped by ALMA now in a number of galaxies. And the chemistry is just beginning to emerge from this. We're going to have a meeting in Charlottesville in April so we can discuss some of the molecules that have been detected in galaxies. But some things that emerged, we had a conference last December in Tokyo, are that a molecule like HNCO is often seen in well-shielded disk gas in the central regions of galaxies. HC3N seems to trace X-ray exposed gas. SIO seems to trace the innermost dense gas, as in fact it does in the center of our galaxy. And these are seen now in a couple of different galaxies. But also, if we have all this mass in the center of a galaxy, we can use it to constrain the mass of a central black hole. That was recently done by Anishi et al. In NGC 1097. And this isn't particularly high resolution ALMA data, here on the order of 2 arcseconds, but they observed HCN and HCO plus towards the center of 1097, and you can see the rotation of the galaxy is clearly evident, and there is a central peak of molecular gas. So it behooves us to look at the velocities in that central peak a little more carefully, and they did that and fitted a black hole to the central object in this galaxy, and in fact it fits the velocities that they observed quite well. The central black hole is measured by them to be in the order of 1.4 times 10 to the 8th, which I believe agrees with other estimates of the mass of this galaxy. So this whole field is just getting started. I expect this to go a long way as we continue. Nearby, here's that ultraluminous infrared galaxy ARP-220 and NGC 6240, as imaged by Nick Scoville with some of the ALMA data. This is an amazing molecular cloud. The size of this molecular cloud is in the order of 65 parsecs. It has a huge stellar mass associated with it, such that the density of the gas in here is already the density of some of the densest molecular clouds that we see nearby, except spread over 65 parsecs here, at least in this nucleus, a little less over here. NGC 6240 is a similar galaxy, not quite the same. So each of these merging galaxies has a central black hole, and presumably in the next tens to hundreds of millions of years, these will merge, and there'll be quite a fireworks show to watch there. Moving closer galaxies, another region that ALMA has had excellent effect because of its ability to look at spectral lines, is to be able to probe the gas kinematics near galactic nuclei. Now, I showed you the black hole there, which is apparently infall. Sometimes it's a little hard to tell infall from outflow, and it's also particularly difficult to associate a mass with the material that you see because your calibration is based on CO, carbon monoxide, and all we know is what carbon monoxide is in normal clouds in our galaxy. An outflow near the nucleus of another galaxy, that may not, in fact, be the case. So in NGC 1413 here, at an angular resolution of 24 parsecs, there were colored structures near the center that reveal a spiral shape. as well as an unexpected outflow that hadn't been seen before. So the suggestion is that the outflow here is entrained by the radio flow, which is known to occur in this nucleus. NGC 3256 is another example. Here the molecular gas might reach 1,800 kilometers per second. Estimates of the outflow are 20 solar masses per year. NGC 1266 is yet another one. Here the CO shows outflow of 500 kilometers per second. It seems to be losing mass at a greater rate. But none of these masses are extremely certain. We need better mass estimators for outflows. So this is NGC 1413. Okay, so nearby, brilliant starburst galaxy that's well known as NGC 253. Here we can measure with CO the blast of material coming out from the center of the galaxy in an outflow, which is greater than 3 to 9 times solar masses per year. And clearly this starburst-driven wind is limiting the starburst activity in this galaxy. So here's a feedback mechanism at work. Okay. Move on from distant galaxies into the last topic here. I wanted to talk a little bit about protostars and protostellar disks and protoplanetary disks. So the cartoon here is that young stars accrete material through their disks. In the center is the protostar. It loses angular momentum by transforming that into a bipolar outflow. Presumably magnetic fields are involved here, but that's an area of a lot of current study. So these structures are very small, about 100 AU in size, and that at 125 parsec distance to the typical protostar is about 0.8 of an arcsecond. So this is a high resolution need. So how does the gas flow through the disk onto the young stellar object is one question. With high angular resolution, we can probe these structures. And as we've done that with ALMA, I think there are a number of interesting features that have come out. So here's the cartoon. We start off with a core. Material is gravitationally assembled into a clump, which we can see as a glowing object with ALMA or as a dark blob against a background of stars optically. Then the disk is formed, from which accretion occurs, powering the jets in the source. And here's an image from the Space Telescope showing one of these objects, HH130, where the disk is this black area down here. And then transitional disk planet formation. Here's an image from ALMA showing the million-year-old disk associated with the young star HL Tau. And eventually, the planets form, and this disk is also dissipated, and there's just some debris left over at the end, and that's an example of that is Fomalhaut, again, another early ALMA image showing a ring of material left around Fomalhaut. Okay, so one of the interesting things I think that ALMA has discovered is the structure of these disks in their midplane. In particular, the midplanes are the site where we expect the planets to form. That's where the density is highest. That's the main reservoir of mass, probable sources of complex organics. They're cold. They're shielded from radiation from the star by the fact that you've got a long path length along the disk to the star, from the interstellar radiation field by the fact that you're at the center of the disk. So they're cold. Ices form. Ices are sticky. These are good seeds for making larger bodies. And so these midplanes are characterized by a range of low energy lines of ions, deuterated molecules, isotopologues, and organics. As you get to very cold gas, deuterium has an energetic advantage in molecules, having a much different mass from hydrogen. And so at temperatures below 25 degrees or so, you can build up the deuterium in a number of molecules. That gives you a good probe for being able to observe where things are cold and also dense. So the observational feature is a snow line that occurs to where the temperature drops, heated by the central star. Now it's not penetrating out through the disk, to where the frost forms. So in this case, CO is beginning to deplete out of the gas at some radius from the central star, where the temperature has gone down to 20 degrees or 15 degrees Kelvin. And so what you observe is that CO, through the chemical reaction with H2D+, which is a predecessor ion to HCO plus and DCO plus. So we can see a ring here where the temperature has dropped enough so the CO is dropping out. We're able to observe the DCO plus. Now, where the CO actually vanishes, then the most strong deuterated line becomes N2D+. N2 doesn't disappear into the frost at nearly the low temperature CO does. So in fact, this is an image from N2D+, showing where the CO is beginning to freeze out in this disk. So there are a couple of cases of that. Here's another one, a different set of lines, actually showing the frost line here from DCO plus beyond this ring. The DCO plus, the CO has frosted out, and so there is no DCO plus. Interior to it, it's not warm enough to make the DCO plus. And so these observers actually observed a number of different isotopes of HCO plus, including DCO plus shown here, to show that this was really mapping out the snow line in the disk, which is where we expect the planets to start forming. So recently, Karin Oberg made this interesting observation of double DCO plus loops in a star appropriately named I'm Loopy. This was a observation of DCO plus. And so in cold gas, as I said, where the CO is present, DCO plus readily forms from a reaction of CO and H2D plus. But in the cold disk midplane, the CO is freezing out of the grains at some distance from the central star where the temperature is sufficiently low, below 20 degrees or so. And so in their model, that happens at 25 AU, and that in fact coincides with this inner ring. So in the blank place here between them, the CO is frozen out. The midplane is still cold there, and there's still H2D plus there. And in the outer ring, where the interstellar radiation field is beginning to penetrate in, it's beginning to liberate some carbon monoxide. That H2D plus interacts with that carbon monoxide to make DCO plus in Karin's picture here. And so we have both an inner and an outer ring. One is the snow line, and one is the no more snow line.
How many AUs is the
Sorry?
How many AUs?
So this is 25 AU across this inner ring here. Okay, so this is all an arcsecond. Okay, and here's the actual data. This is the artist's impression. But I think you can see the loops are definitely there in the original data. So here's an isotope which doesn't show the same kind of fractionation that deuterium does. So you can see the spread of the carbon-13 in HCO plus is much different from the DCO plus. So they made a pretty strong case for this, I think. Okay, I was just going to show a few more of these, and then I'll close. I think you all saw the HL Tau image that came out about a year ago from the Long Baseline campaign. This didn't really have very many antennas involved at that point. We were just commissioning the most distant antenna pads. Remember, I said we only finished ALMA a year ago. And so there were only about 12 antennas on the Long Baseline, so we could do much better than this now. Nonetheless, this is a pretty impressive image. It was not thought that there would be so much structure in a transition disk around a star about 1 million years old as HL Tau is. So the whole solar system basically fits within this inner region here. The resolution element, there should have been a beam on here, but there isn't. This is about the beam, I guess, is about 50 milliarcseconds, so it's quite a high resolution image. Some of these items here, like these, particularly these dark areas, are imaging artifacts caused by the fact that we're observing this at a fairly high inclination angle. And so even with the number of antennas we had, we couldn't sample the whole Fourier plane. So you could do a much better image than this one. But nonetheless, there are 8 or so objects here. Some of the papers have interpreted this as resonances created by some 2 or 3 planets which have been formed and are circulating around in the disk. Here's another example. I just wanted to talk a little bit about these transition disks. We mentioned the gas flowing through the gap. In this particular object, there's an artist's concept. There's a disk that's been known in the infrared for some time. There's a star a little more, about 1.8 solar masses or so, with a disk around it here. And from the infrared, you can see that the accretion onto this central star is such that the disk mass of a few hundredths of a solar mass should be all accreted onto the central star in a year. But it's still there next year and the next year. So somehow it's being fed. So it was known through reflected light in the infrared, scattered light in the infrared, that there's a very large disk around here. That disk seen in the infrared is very symmetric. And we looked at it with ALMA, and it found a very asymmetric horseshoe type disk. And in fact, we found some HCO plus that was apparently streaming from the outer disk to the center disk, showing how that mass might be maintained in the center disk. So here is a three-dimensional view of this complicated data set. This is CO. And so what you see is the fairly stable outer ring here, where you don't see any large velocity excursions. But then velocity takes off and goes to higher velocities. Velocity increases this way and this way, down towards the center of the disk where that central star is, as you proceed further and further away from it. So you can see that gas is streaming through this gap, CO gas is, towards the central object. You'll also notice here an area where the CO is somewhat depressed. It turns out that that's because in the dust ring up at this region here, which is where that occurs, the grains are actually growing because the disks are actually tilted with respect to each other by about 60 degrees. And so the central star actually is throwing a shadow on the disk here. In that shadow, the dust is colder and the grains are sticking together. And observations at lower frequencies, 34 gigahertz, show that in fact there's a big clump up here. So this may show us how things like the shadowing of a disk can lead to clumping of grains, which may foster the next planet. So transitional disks have been one of the big impacts of ALMA. Here we can see disk, two different transitional disks. I may have a different picture now. I guess I don't. And in fact, they're lopsided. And this occurs because in the inner portions of the disk here are planets, which are causing a pressure imbalance between the center of the disk and the outer disk. And so there is a tendency for the large grains to accumulate in a lopsided fashion in the outer disk. This may be accentuated in this case by the fact that this is cooler here and the shadow of the central star is falling on it. The last stage here that I'll go through are debris disks. Debris disk is what's left over after everything else is gone. Usually these don't have very much detectable material in them, but here is one case of a debris disk with a measurable amount of cold gas, which is showing a nice Keplerian rotation here. And it also has a dust-free inner disk and an asymmetric dust region here within 55 AU of the central star. Here's a really interesting object. FW tau is a double M star. It's a triple system. There's FW tau C off here. And so they looked at this with ALMA because there was evidence from the infrared of molecular hydrogen emission here, and discovered a dust disk around the companion. There's nothing apparently around the M stars. But this dust disk has the mass of Jupiter's satellite systems. It's really low mass, but because of ALMA sensitivity, we're able to detect that. So here's a case where we may be observing a satellite system or a planet in formation. I'll just show you the beta PIC debris disk. Here's the continuum image showing a fairly symmetric debris disk in the Space Telescope. But when we looked at it with ALMA, we found that the CO was all concentrated in one quadrant. Here's the ALMA image. Down here, this is unstable. This can't last very long. It's only estimated to have a lifetime in the order of 100 years. And so this must have been formed from something violent happening within this disk recently, perhaps two collisions of two bodies. Okay. So we also observed disks around brown dwarfs. I showed you the one around the Jupiter system a while ago. I'll skip through the last of this because I think I'm out of time. Okay, so we also look at the shells of evolved stars and get to determine the isotopic as a function of distance. And we looked at Pluto. Here's Pluto and Charon. The spacecraft was in fact guided by these ALMA observations, which were able to provide a better astrometric accuracy than was available before, so that they could guide the spacecraft between the two more accurately. And during the long baseline campaign, we also imaged the asteroid Juno at high resolution. So here we get tens of kilometer resolution on the asteroid. So we're able to do a whole variety of science. The next up, as I said, was millimeter VLBI. What we'd like to do is be able to image the black hole at the center of the galaxy. So here are some cartoons showing what we might be able to see. We have, in fact, been able to link ALMA up with other antennas, both at 1 millimeter and 3 millimeters throughout the Western Hemisphere, and we're hoping to bring this online next year. I'm not sure whether we'll be quite up to taking an image of the black hole at the galactic center, but I think that's an exciting possibility. So, after 3 decades of planning and construction, ALMA is approaching its full science operations. It's internationally built and governed. That's excellent for your funding stream. Not good for your politics. Early science has been hugely successful, so regular observing cycles are underway. The next cycle will be in April, and we want further development via community involvement. So we encourage you to use ALMA for your research. Thank you.
Thank you all for staying so late. A little bit, we can do it over time, but
Yes,
that's
I did go
nice to see
on. Sorry about
many
that.
of you are still here. So we
Yeah.
have time for a couple of questions.
And I'll be around for the rest of the day.
Yeah, and he'll be, Al is going to be here today and tomorrow morning. And yes,
Yeah.
there's one question.
Please.
So could you talk about other future developments of ALMA that are in the pipeline other than just combining the total power from the antennas?
Right. So what we'd like to do is be able to build those extra receiver bands to upgrade the correlator. Those chips in the correlator were built in 2003. So we could double the bandwidth of ALMA, double the spectral grasp, if you will, the number of spectral lines we can detect, double the continuum sensitivity. And so that's one of the development items we're pursuing. Others are in the software line. And so we have a University of Maryland-led consortium which is going into the ALMA archive and looking for spectral lines. See, when you observe with ALMA, you get 3,840 channels, and you might only be interested in a CO line that occupies 120 of those. So that's all we image and send you. But there might be a lot of other spectral lines in that data. And so the idea there is to go through the archive, image all the channels in the data, and then to produce moment maps, line identifications and moment maps of those that will then be in the archive to help guide potential users to interesting data that might be hidden there. So those are a couple of the developments. Of course, to have a correlator with a wider back end, we have to upgrade the digital conversion at the antenna, so there are a number of different things there. But I think those are the most exciting things that are coming along.
I want to stress also that you're theorists and you really want to look at an object. ALMA is really a fantastic instrument because they basically do all the hard work of reducing the data. They make all the Fourier transform and they make the images and then they send it to you and you can look at it. So you have a lot more time to really model the data than other interferometers where you really have to do everything from bottom up, and it takes enormous amount of time. So this is really a great opportunity for people who are interested, and they're not necessarily observers, hardcore observers, but they can actually spend more time thinking about the object that they're interested in.
So let me just put an ad in here. We have an archive. Farhad and I were just struggling with it as he got delivered his data today. It's not the most user-friendly archive in the world. It's at almascience.org. However, the Japanese have built a much more user-friendly input to the archive as part of their virtual observatory. So if you want to look for some specific object, I urge you to Google Japanese Virtual Observatory and go to the ALMA, and there you'll find a nice list of objects, RAs and DECs, and each one is linked to a data cube and a little visualizer that can allow you to see both the image and the spectral line that comes from it, which is somewhere we aren't quite yet with our archive.
Okay, great.
Quick question.
Yeah.
Earlier in the talk, you talked about plans or potential plans for taking different radio telescopes around the world and linking them up.
Yeah.
Would that require some brand new technology at the correlator level? I mean, how would that actually be?
Yes and no. I mean, that's all being driven by an NSF grant to Haystack. So Haystack's leading it. So they have a next generation correlator that in fact is more advanced than what we have at the Very Long Baseline Array in Socorro. And so right now we're coming up with a model for how the data will be correlated. right now the straw man is that that data will be correlated at Haystack and then go back into the archive as correlated data. But there's no general agreement on that, and that's one of the political problems we have with ALMA, is trying to get everybody to agree. So, you know, you have to involve the individual antennas. Lucy Zuras will be here later on. Perhaps you know John Carlstrom as the South Pole Telescope. You know, we have to bring them on board with this plan because we'll be using their telescopes.
Okay, great. Well, thanks for all of you, and thanks, Al, for a nice talk.
Yeah, thank you very much.